Okay. Just so welcome everyone to the neural computing class. So this is a hybrid class lah. So you guys here we have about, let's see, 50, 49 about. So the rest of you guys are online, right? So just checking to those who are online, can you hear me?
Yes.
Yeah. Okay. Thank you. Thank you. I mean, if you are here, reply me yes. It's a bit funny lah. Okay. Just I understand. It's a kind of a new thing, right? So not familiar, but yeah, let's have let's kind of enjoy this journey. So today we'll welcome back from the semester break. So this is our first face-to-face, not face-to-face, a hybrid class lah. Yeah. So it's actually, I'm not sure about the policy actually. Some classes are strictly face-to-face. I've been made aware of that. Yeah. But I think considering the difficulties, if you want to rent a place for just 3 months, it doesn't make sense because you're having semester break after that anyway, right? So we'll do a hybrid class. So from this week onwards, as I said before, right? The slides are pretty much over, right? And most of the slides I'll be using from the Sebastian Rashka, from I think he's from University of Madison or Wisconsin. I'm not sure. But I think I've given you the site, the reference site for that. So I'll be from time to time I'll be referring to his slides as well. Yeah, and of course I'll be using the Google Jamboards and as well. So for today, as just a very soft starter, it's just because we are from the break, right? So I don't know, maybe you guys from Balik Kampung, anything, I don't know, right? So we'll just continue with exploring the MNS IST dataset. Just talk a little bit. So today is a bit of a warm-up session lah. Yeah, nothing heavy. Seriously, nothing heavy today. Yeah, maybe I think I understand that most of you guys are also quite advanced in deep learning because you've learned yourself. Some of you might have taken a course or try to learn yourself or something, or do some self-learning or something like that. And this might be boring, but I think it's necessary for those who are totally new to this deep learning course. Okay, so I've talked about the MNIST data set, and of course we have a where's it again? Yeah, so this is one of the how should I say, the leaderboard, I guess, yeah, the leaderboard that keeps scores of what is the best state-of-the-art model, right? So, for example, for MNSC. But as often as many of the available boards out there, right? Most of them are, what should I say, maintained personally, right? So they are not like companies running. So these are like personal people, you know, most probably they are graduate students doing masters or PhD, okay, doing masters or PhD, right? And they are maintaining this board. So who is the best at MNIST or CFAR 10, right? So we have uh, some papers and works, and what is so they interpret their work rather than prediction accuracy. Is more, as I mentioned before, they use error rate, right? The error rate, which is of course 100 minus the prediction accuracy lah, right? As simple as that. So right, so, and I mentioned before that MNIST, we have there is a paper, right, I showed before, which achieves 100%, right? They are using a method called signature transform. I haven't got my head around the methods anyway, right? It's a kind of it comes from a mathematic domain, right? I think it's called a rough path. So anyway, if you Google signature transform, there is a kind of a whole mathematical domain on it, right? So we have, I don't know, signature. Transform. Yep. Deep signature transforms. So this is our, oh, sorry. I haven't shared my screen for those who are online. Yeah, I need to share my screen. Okay. So this one. Yeah. So for those who are online, if I haven't shared my screen, please tell me. Yeah. I'm just keep on talking. I'm actually sharing my screen. So these are the techniques that is being used in the paper that achieves 100%. Right? In the paper that achieves 100%. And even though tested with validation, so some people like Sebastian Reshka and their team are validating the papers, the work, where this, you know, because usually many times, right, in deep learning, in AI, as you probably know by now, people make exaggeration claims, right? Okay, we have achieved something where we have something, but not really the case, or for some very specific unique cases. So in these cases, it seems like, yeah, so far, it seems legit, right? It seems legit so far. So yeah, that's impressive. And it doesn't really have like if you look at the codes, right? It doesn't really have like a training or backpropagation or gradient descent. It's more on to somehow calculating the errors. I'm not sure, the error rate or some statistics, right? Based on some equations. But okay, but you can have a look at that. But we're not going to talk about signature transform. Today we're going to talk about the MNIST just a little bit more. I've uploaded this on the GitHub, right? Just to get things started. As you know that there are many codes online, lah, right? MIT is publishing their codes online. Stanford are publishing codes. Many places are publishing their codes online. So you can get many codes online there. That's fine. But the point here, now that we have this MNIST data set, right? How do we do that in PyTorch, right? Of course, we download the data set, right? Using the Torch Vision library, right? It can take a while to download, depends on your internet connection, using Collaboratory. But the problem is with Collaboratory, once your session runs out, disconnects, you have to run again your collab, right? And if you're doing on a local machine, right? You just download it once, lah, right? Then you can, there's no problem, okay? So that's fine. And the data sets, we are looking with Torch Vision data sets, but as you can see, we have PyTorch have, the audio libraries, the audio documentation, and you also have the Torch text, right? Torch text, and of course, PyTorch, the website itself has lots of tutorials and documentation on how to do things. So these are Torch texts and classification, language modeling, machine translation. So have a go at this as well. So for example, this is our this is from the PyTorch tutorial, right? This from I haven't uploaded this. It's from PyTorch tutorial. It's for using the text classification with Torch text library. Just some examples of how of the things that you can do with PyTorch, right? So PyTorch has its own data sets. So you don't have CIFAR 10, things like that. But you can also customize. You can also have customized data set, right? You can also have customized data set. Let me have a look. Never mind lah. Okay. So as you can see, if you do this data sets. Yeah, so you can have lots of data sets here. Just just need to choose lah. And lots of yeah. Okay, so you have Caltech 256, CIFAR 10, and all that. Does it have ImageNet? It should have ImageNet. Yeah, we have ImageNet. So if you are comfortable, if you are familiar with ImageNet, ImageNet is a database of 14 million images, if I'm not wrong. 14 million images. So that's quite a lot, right? And the ones that we are dealing at the moment, the MNIST, is very small, relatively in deep learning. It's very, very small because you don't have to use GPUs anyway. You can use CPUs. The difference is not so big. Okay, the difference is not so big. So if you are downloading the data sets, of course there are many data sets that you can use. Then of course if you want to in many cases you want to say, instead of data sets, just you want to specify what is this training data sets or a test data sets, right? So if you're using training data set, you set the trained variables, the parameters as true, and you download it. This is the types of data sets that you can download from Torch Vision. And now that we've downloaded the Torch Vision data sets, let's just explore the data set a little bit, right? So how, before we effectively implement an multi-layer perceptron. So on Wednesday, we're going to do multi-layer perceptron on the MNIST dataset. Okay, so yeah, probably for those who are familiar, right? Well, this is basic, right? the child's play of deep learning, right? You are using the MNIST, nothing interesting, nothing advanced, nothing new. But for those who are totally new, this is probably the best place to start, the easiest place to start. Anyway, so you want to try to explore the data set. We can visualize the data set. For example, I've just visualized the first 10 images, right? First 10 images. As you can see, it's just handwritten digits, right? Handwritten digits. We have another MNIST, the eMNIST. You're familiar, the extended MNIST, which is a data set which consists of not just handwritten digits, but also alphabets. So here in our data set, the MNIST, we only have digits, 0 until 9, right? The different ways of 0 until 9. But the eMNIST, you have A, B, C, and capital A, small a, lowercase a, and all that, right? So uppercase, lowercase, and all that. But no symbols lah, right? We don't have symbols. We only have the alphabets and the digits, okay? So here are the data set, and one thing that you want to do is you want to have a look at the data set. How should I say? Just a moment, yeah. Let me run here. Okay. So your data set, you can have your classes, your data here. And of course, if you're applying transformation to your data set, for example, you're doing normalization as well, or you're rotating it, or you're flattening it into a vector, these are the information that you pass it through, right? There are many. So you want to kind of explore the data set as well, right? The data set object in PyTorch. So this is okay. This is how you visualize the images, things like that, blah, blah, blah. So, so what is, you want to have a look. So the data set, this data set stores both the label and the data, right? So for each data, for the data set object has its own labels and data. So you want to have a look at how do you look at the data set? How do you look at the labels? Which are the training data set, or which are the test data set? Of course, once you have a test data set, you just need to go back here, right? You want to do, for example, you can usually, right, when we'll do this later, right? We'll do a training data we'll do a train data set and test data set, and then this just falls through, and then probably you apply some transformation here. Okay, so these are, you want to have a look at the labels as well, right? You want to have a look at the labels. What kind of labels do they have in this example? So how many instances are there for each label? This is the data set balance. This obviously we have the data. If you Google around, you probably find this anyway, right? You'll find this information anyway. But let's assume that you don't have that information, right? So have a go and code how many instances are there for each label. Is the data set balance? So this is the answer. I'll just give you the answer, right? So you have to code and see if you get the same. So that's our tutorial for today, right? That's our tutorial for today. So the number of instances for each classes, right? For label 0, and 2, 5, 6, 7, 8, right? And we have we just want to check whether the data is balanced or not, because we don't want classes or labels which are too underrepresented or overrepresented. We don't want in an imbalanced data set, right? So that's kind of a, it's kind of a tricky. So this is a kind of a tutorial for today. Just a quick, maybe 10 minutes for you guys to solve it, right? See if you can get the same numbers that I do. As you can see here, number 1 is overrepresented slightly, just slightly lah, right? About 11%. And number 1, 3, and 10, I guess, right? The others are about 9%. So, and that is all for today. Yeah, that's all for today, because the next part will be going for the implementing the multi-layer perceptron. Probably I'll touch about that a bit. Yeah, probably touch about that a bit today. So for the next 10 minutes, maybe you want to have a go, right? I'll just give you some time to have a go and see if you can get the same numbers. Okay. So the idea is for you to play around the data set object.
Just dangle.
I'm gonna angle you. So you don't get taken.
Alright. Where are we landing?
Left side.
Left side rock.
Look at rock. Look at rock. Look at rock.
No bubble.
No bubble. Shoot left.
Yeah, put back. On the right. Bubble 7 seconds. It's still on. Like bubble 3, 2, 1. Bubble.
Bobby, make it.
Walting. I walked. Push right. Back to me. You can use me. That's my ulti. Let's go crazy. Behind you. Oh my god. Get the fuck off of me.
不管有地与我，但愿你们安然生存，像适合的灵魂，共度余生。我们太久没见了，可能太远太近太深太浅，不懂得舍不得，不舍得，情绪交错了。我们太久没见了，可能还是注定擦肩就这样错过。如果我抱紧。
Here, I think he might be moving into where we're at.
I might be. Yeah.
Maybe, potentially.
I'm checking the place out right now.
And then he's gonna quit Valor for Apex.
Yeah, dude, I'm bronze 1 right now, bro. I'm on the.
Get the fuck out of my room. Get the fuck out of my room. You're gonna be the hardstack 10Ks that cause me problems, bro. I fucking love you, buddy.
I love you,
I love
dog.
you. I'll be out in like 2 minutes too.
Yeah, go for it.
I love you, bud. Yeah, he does the goat. He's like the fucking man. He's like the fucking man. Okay, wait. Let's watch this back again. Let's snipe down real quick. Chad, he's gonna be hardstack 10K. He's gonna ruin all my fucking games. Ready?
Try and get eyes. Don't let these guys res. We can clear this. We need to clear this.
All dead. There's one more right here on the left side.
Is it a full team or?
I don't know. Shiny, come here. Shiny.
There's only one red. I'm coming.
Oh, he's almost chill person out of mental health.
Yeah, we probably should.
I swear to God. Watch this, shot. Watch this.
He's in the corner right here.
Did not hit you in the fucking back.
It's actually so bad, dude. It's actually so bad. It's actually... It doesn't even look like it hits him, man. I think it hit the gun. No, let's go to the top this week. Hard to swallow pills. You being dropped for a better roster is always due to lack of performance. Why do I feel like this is going to backfire on him soon? It will, and I'm screenshotting it. So, I think they're in for a little bit of a... I think that aged pretty poorly on those comments. For sure.
I want audio. Safe pred right now is 24,000.
Okay. Done, huh? Hopefully. Sorry? We haven't done this, the The second. Okay. Okay, I'll give you another 5 minutes. Sure. Right. Just meanwhile, for those who are still doing it, just continue lah. Right. So I'll just be talking a little bit about the custom data sets. So as you can see in this course, we are using what we call a toy data set. So things like MNIST, CFR10, even ImageNet, we can call it like a toy data set lah, because in a way it has been cleaned, it has been processed by some other people, and some in many cases, in many types, these types of data sets are ordered, and they are in many cases already shuffled for you randomly. So it is not, you have to do a lot of pre-processing. But as you embark on your journey for your FYP, even if you're doing internships, right, you would realize that the data set that you'll be facing, or the real world data set, is very, very much noisy. It has lots of noise, it's unlabeled, it's a mess, basically. It's a mess. So in those cases, like most of you probably know by now, a lot of time that you have to use a lot of your time in order to get the data set arranged, or you have to clean your data set properly. You have to prepare your data set. Most probably there are cases where you spend 80% of your time preparing the data set, right? Because the design of your model, once you design and once you implement it, you just need to you have to study a little bit on how to find the right architecture or the right network and optimize your model. So that doesn't really take as much as time and laborious as you're preparing the data set. So if you're trying to prepare your data set in PyTorch, you can write your own custom data set. I think the two important parts in custom data set is the lang item and the get.item. Get item. I'm not sure where it is. It should be in the class. Right? Yeah. So these two is probably the most important, not the most, the essential part of your custom data set, right? And once you have your data set, then you will, once you have prepared your data set, then you will upload your data set, or not upload lah. You will transfer it. You will be using a data loader, right? Data loader. So this data loader takes care of your batches. So if you remember in the SGD assignment, right? So I asked, so I don't know how many of you did the mini batch, right? Mini batch assignment. So I asked you to do the stochastic gradient, the SGD, and also the batch gradient. So if you're using the stochastic gradient and the batch gradient, that's fine lah. And it's not really well. It's mini batch is also not that difficult lah. But if you have to handle mini batches, right, then you have to specify the size of your mini batches. I don't know, maybe 64, 128, whatever, right? And then in order for you to train through the mini batches, right, instead of having another for loop or something, you can use the data loader. So in the multi-layer perceptron, when we are implementing the multi-layer perceptron to classify the handwritten digits of the MNIST, we'll be using, so these are the steps. This obviously this is, as you can see, these 10 steps or 11 steps. That's it. That's it to the most. That's the basic thing lah. In order for you to train a neural network, right? Most probably, even CNNs and RNN, these are the basic stuff, right? These are the basic stuff. And unlike your SGD assignments, right, you don't have to worry about backpropagation anymore. Everything is done by loss.backwards, right? So autograd. So autograd, PyTorch autograd takes care everything on that part. Yeah. So these are the main steps. So you have about 11 steps, right? From setting, of course, you have to import the libraries. You have to set the data pre-processing, how you want to transform your data set, and you have to split your train and test. And of course, what else? Train and test, and another one is validation. Yeah, if you probably want to validating your data set is probably or your network is probably a good idea. Okay, and then you have the data loaders. Now the data loaders take care of your mini batches in a way. Yeah? In a very broadly speaking, I'll say that, right? So you don't have to worry about, how if you set your batch, for example, if you set your batch to 128, or you set a batch to a bigger, the size of a batch, or your mini batches to a bigger number, then you have to, change or something. You don't have to do that. Yeah? You don't have to worry about that. And of course, the data loaders, it takes care of the shuffling. It shuffles your data set. Yeah. So it shuffles your mini batches lah. Right. Your mini batches are also shuffled by the data loaders. So you don't have to worry about that. But as you can see, as you will see in MNIST, MNIST is a very, very clean data set. I don't really like to give you those who are familiar with deep learning, right? MNIST, because it's not challenging. It's not challenging. There's nothing much you can, because it's already clean and all that. There's nothing much you need to do, right? But those who are totally new to deep learning, is very nice lah. You have a clean data set now. Okay, so data loaders take care of your the mini batches and also the shuffling of the mini batches and the data in the mini batches lah, right? So in our I've just make a poll. How many of you have heard about the universal approximation theory? No, none. None? Okay, so what is this theory about? So if you, this is a, MIT has a introduction to deep learning course, right? This is a non-mathematical talk. It touches briefly about universal approximation theory, okay? But I can tell you in a sense what that is. Right, in that is meaning that I'll have to use just a moment. I have to use the tablet and write on Jamboard for those who are online. Right, for you guys, I can write on the whiteboard lah. But we have students online, so just take a while. This is a very, very rough explanation about what is universal approximation theory is about. Okay, so if you kind of Google around, right, there's of course universal approximation theory. There's a Wikipedia page, of course, obviously, right? And lots of maths here, maybe if I have time, I'll probably go through this with you if I have time, right? I'm not sure if I do have time or not, right? So basically, universal approximation says, approximation theory says, if you have a network, right? So this is your x1, x2, blah, 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 xn, right? And this is your input layer. And this is your hidden layer, right? And your hidden layer can be huge, right? You can have this is called a shallow but wide network, right? You can have deep but small networks, or you can even have deep but big networks lah, obviously, right? Okay, you can have lots of and also you have, for example, you have just maybe two outputs, y1. This is a multi-class, so this is your output. So what does it say? Blah 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 blah. Right, that's it. This is so universal approximation theory. Well, you can go to the MIT talk and listen to it as well. It kind of explains a universal approximation theory as the new frontier, not the new frontier, in the concept of the new frontiers, right? So, but I'm gonna save your time, right, by saying that we can say that is any function, how should I say this? Not function, arbitrary function. Right? Like I say, arbitrary function can be approximated. This is oversimplification, oversimplification of things, right? At the risk of oversimplifying things, I'll say this. Can be approximated by a network with only one hidden layer. I think this is remember the tutorial on perceptron by, who's that guy again? Kwok, the Vietnamese guy, from Google Brain, right? I think I have given you the PDFs on it. So the John and the Mary, and you have to classify the movies whether you like it or not, right? So Kwok V. Lee, I think, right? It's his name, right? Google from Google Brain. He also talks a little bit in that tutorial. He also talks a little bit on universal approximation theory. So basically, so the idea is like this. You only need only one hidden layer, only one, this guy, and it can approximate any arbitrary function. This is the theory lah, right? Whether it's true or not, that's another case. That's another case, right? And it has been shown, right? Quite a lot of functions can be approximated using only one hidden layers, right? So your network, the idea is your network doesn't have to be doesn't necessarily have to be very complicated or complex. The idea is for you to simplify your network as you best, as best as you can, right? Because you know, complex models is nice, but a simple model is better. It's always better. That's the idea of it, right? So any arbitrary function can be approximated by a network with only one hidden layer. And our MLP, right? We are doing a multi-layer perceptron. What does a multi-layer perceptron means? It means that it's fully connected. We're doing a fully connected multi-layer perceptron, yeah, for classifying the MNIST handwritten digits. So all our nodes are connected, so units are connected, right? So we'll be doing that, and we only have one hidden layer. We'll do with one hidden layer for simplification's sake, right? Maybe you say, so before you ask me, Doctor, why only one hidden layer? Are we supposed to be deep learning? Why not we do 2, 3, 4, 5, 6, 7, 8, 9, 10 layers? Or maybe like ResNet, you know, they're very, very deep layers. You can have 50 layers, right? You can have 50 layers, right? Or you can have like Kwok V. Lee says, right? Some layers you can have these kind of layers, right? XN, right? But the hidden layers are small, but you have lots of them. So you have a deep, but not, the hidden layers are not very big, right? And then only you have the output. As opposed to this, so this is we call this is a shallow network. Shallow but wide lah. But wide. Right? So we want to have a can we do that? Right? Can we do that? So let's just try that with our MLP, right? So we'll be doing that on Wednesday. And we'll go through the all these 11 steps. Right. So the idea is for you to, of course, like I said, there are so many codes online, right? All you need to do is just go through all the codes. But then obviously us being humans, just because they are online, we're not necessarily we're gonna do it, right? So let's kind of take this opportunity to kind of do it together, right? And go through the together. Okay. So if you have any questions, please ask me. And that is all for today. Yeah? So as we will be seeing later in our next classes, we'll be doing the transformation. We'll be using the data loaders. We'll be doing some exercise, a little bit of exercise, and this is the most important part. We'll be defining our neural network class. Right? This is where you define the neural network class. Unlike TensorFlow, or most probably sometimes I don't know, maybe some of you before this. You just, when you're using TensorFlow or I don't know, some scikit-learn, you're just calling the network, right? Multi-layer perceptron or CNNs or something. Here you are customizing. How many layers? How many hidden neurons? what is your activation function, right? Are you going to apply dropout or regularization, right? I'll talk about probably next week, not this week, next week's lecture, probably talk about the optimization and the regularization. So the dropouts and the optimization is the Adam momentum gradient descent, and the regularization is the dropout. This is the dropout lah. Okay. All right. That is all for today. Thank you very much for coming. It's kind of refreshing to see all of you. I haven't done this like in a while, 2 years. So hopefully to see you. Next week is holiday. If I'm not wrong, on Monday, Wesak Day. Kan? So Wesak Day. So we don't have tutorials on that. I'll be releasing the assignment sometime this week lah. Yeah? I'll try that. Kan? If I'm late, I'll do it on the weekends, right? So you can use the Wesak Day to work on the assignment or something. Okay. If you have no other questions, that's all for today, right? Thank you very much and see you in another 2 weeks, right? Okay.
Thank you, Dr.